Section 7.4, complex rational expressions. Okay, in section 7.3, we have learned how to look for the least common denominator and how to do the addition and subtraction of rational expressions. And in this section, we are going to look at another special type of rational expressions. See, when we have rational within rational. So look at this expression here. We have a numerator here, a denominator. But within the numerator itself, we see two more rational expressions. And within this denominator, we see another rational expression. So if we have some expression like this, we have rational within rational. They are called complex rational expressions. And this kind of expression is not allowed to stay as a final answer. When we have some expression like this, we have to simplify them into a regular rational expression, which means we'll have a numerator and polynomial as a numerator and a polynomial as a denominator, a regular rational expressions which cannot be simplified anymore. This is what we want. So now how can we make this happen? Actually, we have all the ingredients already. We just need to put them into a new meal. So how do we simplify a complex rational expression? We just need to follow a couple of steps. Number one, look for the least common denominator of all the denominators within this rational expression. So look at what we have here. We check the numerator and denominator respectively. Let's see, within the numerator, I see one denominator x. I see another one x squared. And then that's all. Then I move on to the denominator. So within this denominator, I see one denominator. So within the entire denominator, I see just one denominator, which is x. Okay, so totally there are three denominators. What I'm going to do first, I'm going to look for their least common multiple, which is also called their least common denominator, LCD. What do we do? So recall we did in section 7.3, there is no coefficients. Forget about the numbers. Then we look at the variable. There is just one variable x. So their least common variable will be the variable x with the maximum exponent. This one is 1, this 2, this 1. So 1 to 1. One number is maximum 2. So x squared is the least common multiple. Okay, so having this in our mind or work this on the scrap paper. Now we go back to the original problem. What do we do? So now we are going to do, so having the LCD right here, I'm going to multiply every term in the numerator and denominator respectively. See, I'm going to rewrite this rational expression and spread them out. The first term in the numerator is 5 over x. Okay, so I multiply this by x squared. So I use another pen, so multiply by x squared. And then subtract the second term, 7 over x squared. So this one also multiply by this LCD. Okay, and now let's look at the denominator. So the first term is 6. The 6 does not have a denominator. Do we have to multiply this as well? The answer is yes. So every term should have the same right to multiply that LCD. And the last one is positive 1 over x, and then times x squared. See what I just did? The blue pen represent the original rational expression. And the red pen represent what I just did. I multiplied every single term by that LCD. So why I do this? See, if we multiply everyone by this, we can simplify. So look at the first multiplication. If I multiply a rational expression by another polynomial, what do I do? So this is on the bottom, this is on the top. We always do the division. X squared divided by x. What does this equal to? So x squared divided by x, we'll have the x left. Then 5 times x, 5x. This is a product of the first multiplication minus, and simplify the second multiplication, always divide. X squared divided by x squared, those two cancel out. The ratio is 1. 7 times 1 is 7. Write down the 7. Then continue. So move on to the denominator. We multiply the first one, and there is nothing special. Just multiply those two. 6 times x squared, 6x squared. Then plus, when we have this multiplication, always remember this one is on the bottom. We'll cancel some part on the top. X squared over x. What is left? We have the x left. So plus x. All right, so then when we have this rational expression, we found out there is no more denominators within the numerator or denominator. They're all gone. What we have is a regular rational expression. We just need to make sure there is no way to simplify this anymore. So how do we do this? Try to factor the numerator, denominator respectively, and then cancel the common factor. We'll see there is nothing to be canceled out. Final answer. Okay, this is a typical example how to simplify a complex rational expression. Now let's look at a couple of other examples. This one, what do we have here? We have just numbers. Same thing. Look at what we have in the numerator, denominator. Write down all the denominators. Do this on the scrap paper. I see 6 is one denominator. I see 2 is another denominator. I see 9, I see 3. So there are 4 denominators. How do I look for their least common multiple? Factor everyone respectively. So 6 equals 2 times 3. 2 is still 2. 9 equals 3 times 3, and 3 equals 3. So factor each one completely. Then write down their least common multiple or the least common denominator. We'll use every factor. The maximum time appear in each factorization. The first number I see is 2. So LCD equals 2. How many 2's are here? 1, 2, 1, 2, 0, 2, 0, 2. So the maximum times is once. So I will have just 1, 2 here. So remember, I'm not counting the total. I'm looking at in each factorization, how many times does 2 appear? 1 time, 1 time, 0 time, 0 time. So 1, 1, 0, 0, 1 is the biggest number. So it will appear once only. Then I look at the other factor, so times 3. How many 3's shows up here? 1, 0, 2, 1. So there are 2 3's. There is 1 1. There is 1 3. 1, 0, 2, 1. What is largest number? 2. So then 3 should appear twice. Multiply them out, I get 18. So 18 is their LCD, or the least common multiple. Having this in our mind here, move on to the original problem. Equals, remember, spread the terms, multiply everyone by their LCD. So 5, 6 times 18. This minus 1/2, okay, then times 18 as well. And on the bottom, 4 9's times 18, and plus 1/3 times 18. So remember, do the same thing to every single term. Then simplify. How do we simplify? Divide. 18 divided by 6. We have 3 left. So 5 times 3, 15. They subtract. 1/2 times 8, 18. 18 divided by 2. We have 9 left. 1 times 9, that's 9. Over to this multiplication. 18 divided by 9, what do we have? 2. So 4 times 2, 8. And the last one plus 18 divided by 6, 3, that's 6. 1 times 6, that's 6. Then work on the numerator, denominator respectively. 15 minus 9, that's 6. And 8 plus 6, that's 14. Okay, so 6 over 14. Can we leave the answer like this? The answer is no, because this number can be simplified. And 6 and 17, so 6 equals 2 times 3. And 14. 14 equals 2 times 7. So 2 cancel out. We'll have 3 sevens left. Final answer. Same idea. So this is a complex fractional number, a special type of complex rational expression. Okay, special case. Special case is this. So when we have a complex rational expression, what do we see? We see both the denominator and numerator. There is just one denominator within them. So the entire numerator is just one rational expression. The entire denominator is also just one rational expression. So for this one way, we can still use the method we just did here. Look for the least, so write down the two denominators, 15wz squared and 5w to the third power z here. Look for their LCD and then multiply both the numerator and denominator by the LCD. So this is one method. There is another method here. Whenever we see this complex rational expression has just one term in the numerator or denominator respectively, we can treat this as a division. So this problem is actually can be written as the numerator, 12x y squared over 15wz squared. That's numerator. Over means what? Divide. Divide by the denominator, 18xy to the third over 5w to the third z here. So we turn this complex rational expression into a division problem. Recall, so how do we do the division? We turn the division into multiplication. 12xy squared over 15wz to the second times what? Times the reciprocal of the second expression. Flip that over. 5w to the third z, 18xy to the third. So when we multiply, and we can just multiply them. Numerator times numerator, denominator times denominator. Then we are going to see cancel. Do we see anything in common? Okay, so I see 12 and 18, both of them can be divided by 6. So divide by 6, I have 2 here, and this one I have 3. Just look at the number. 5 and 15, both of them can be divided by 5. 5 divided by 5 is 1. We don't have to write it. 15 divided by 5, that's 3. So cancel the coefficient part. Then look at the variable. I have x here, I have x here. So x, they cancel each other. Then I see y. I have y to the second over y to the third. Remember, when we have apply the exponential notation rules, and we do division, we keep the variable, we subtract the exponents. So 2 minus 3, that's -1, but when we flip it, or another one here, we just cancel. When they have the same variable, we are going to divide by the one which has the minimum exponent. So y to the second, divide by y to the second. This term is gone. This factor is gone. Y to the third, divide by y to the second. We just subtract that exponent by that one. And we'll have 3 minus 2, that's 1. To the ones, we don't need to write it. So we have the y right here. The next variable is w. I have w to the third over w. So using the quotient rule, we have w squared left on the top. The last one is the z. So we have z on the top, z squared on the bottom, z over z squared, we have z on the bottom. So having this down here, finally, we put the final answer down. 3 times 3, that's 9. We have z times y, follow the alphabetic order. Z times y is yz. On the top, we have what? We have 2 left, and then we have w squared. X is canceled out. This is the final answer. So this is a special way when we have a complex rational expression, when there is just one term in the numerator and one term in the denominator. So we do not have one rational expression either add or subtracted by another one. There is just one rational expression. We can treat this as a division. Once again, let's look at one more example. And have many rational expressions in the numerator, just one. So one rational expression over another one. What do we do? Treat this as one division. X plus 5 over 5x divided by x plus 2 over 10x squared. Then just work on the division. The first rational expression remains the same. Multiply by the reciprocal, 10x squared over x plus 2. So this one turns into numerator 1 times numerator 2, divided by denominator 1 times denominator 2. Then try to simplify this. And so 10 divided by 5, we have 2 left. X squared divided by x, we have x left. And there is no more in common, and we just write down the leftover. So 2x parenthesis x plus 5. See, look at what I have here. This is the convention. If we have a polynomial times a monomial, normally we write the monomial in front of the polynomial. And over what? Over the denominator is x plus 2. Final answer. Last example. So what do we have here? We have a complex rational expression, but this time within the numerator, there are 2 terms. Within the denominator, there are 2 terms as well. So then forget about the division method. We have to use the regular method to write down all the denominators that we see. In the numerator, we see one denominator, a squared. So this is the denominator. Within the denominator, I see another denominator, a. So a squared and a are the 2 denominators within this complex rational expression. Then I want to look for their LCD. One variable, then the maximum exponent will show up in their LCD. So LCD equals a using the largest exponent, a squared. So having this in our mind here, go back to the problem. Equals, spread things up, 1 over squared times 1 over a squared times a squared, minus 16, also times a squared. So remember, even though this one does not have a denominator, it has the right to multiply the LCD as well. So every term has the same right. They have to multiply the LCD at the same time. Then move on to the denominator. I have 1 over a times a squared, and the plus with the plus 4a squared. Then just to simplify, for this first multiplication, a squared, what do we have? Those 2 cancel out. We have 1. So 1 minus 16, a squared. Then look at the bottom. What do we have? We have a squared divided by a. And a squared divided by a, I have 1a left. So over a and then plus 4a squared. So this is what we have now. After we multiply every term by the LCD, we have removed all the denominators within the original numerator and original denominator. See, this is just one polynomial over another polynomial. But remember, and we have said all rational expression has to be in reduced form, has to be a simplified rational expression. So look at what we have. We'll try. Are we able to continue to simplify this rational expression? What do we do? Just try to factor the numerator and denominator respectively. So can I factor the numerator? It turns into, when I see this, I see 16. Alert, 16 is 4 squared, and 8 squared is also a square number. So 1 can always be seen as 1 squared. So squared minus another square number, because 16a squared can be written as 4a parentheses squared. So this problem, this numerator is actually 1 squared minus 4a parentheses squared. Difference of squares can be factored as sum times difference. So add the two bases, 1 plus 4a, and then subtract the two bases, 1 minus 4a. So this is what we learned in section, no, actually in chapter 6. That's why I say chapter 6 is the foundation. If we don't know how to do the factorization, we won't be able to do the problem in chapter 7. So here we factored the numerator as 1 plus 4a times 1 minus 4a. Then look at the denominator. We have a binomial, all right? And whenever we do the factorization, what should we check first? JCF. Is there a JCF between the two terms? A, 4a squared? Apparently, both of them have a. So a is a JCF. Then factor the JCF out, a divided by a, that's 1. 4a squared divided by a, we have 4a. So the leftover goes to into the parentheses. I have 1 plus 4a. Now we compare the numerator denominator. Do we see anything in common? Yes, I see 1 plus 4a. I see 1 plus 4a. Now those two cancel each other. I have 1 minus 4a left on the top. I have a left on the bottom. Final answer. So this is the simplified rational expression coming from this complex rational expression. So again, before I end the class, I just want to stress this again. Whenever we are given a problem, we have to guarantee the final expression is a simplified form. Always try. If we cannot simplify, then leave it in that form. If we can, then we have to simplify the rational expression like this one. Okay, so that's for section 7.4. And those two sections, 7.3 and 7.4, are two very challenging sections. You need to practice a lot until you are able to, solve the problem quickly and correctly. If you need extra help, if you want to do more practice, email me. I will be happy to give you more practice problem. Okay, so that's all for today.